Hello everyone, myself Kirish here with Solidworks simulation tutorials. Introduction to static analysis. We'll take the wrench into account and we'll do the simulation. Here the agenda is to deal with the static analysis and the different types of meshes available, and we'll also go through pre-processing, processing and post-processing stage and results, uh, validations and all. We'll cross-check the same. So here we'll do the static analysis on this wrench. Okay, by using the Solidworks Addin you can activate the simulation tool. So by using new study you can define the study name as well. So here I'll simply deal with only the static analysis. Okay, so with that, in the feature manager tree you'll be having the material definition and all the boundary conditions. To apply the material you just need to select the apply material tab. From there it will directly switch to the material library. Okay, there are different types of material available, that is carbon steel, and you can just change the unit system there to MPa megapascal. To cross check, you could see alloy steel, it has the yield strength of 620, so later on we can just cross check with the same material. And then we have the cast carbon steel of 248, plain carbon steel 220. And then so if you want to customize your particular material you can simply copy the any existing material, or else you can start from the scratch. And here you can use the custom materials and just simply paste it and make the changes. So once you add it here you could see each and everything you can modify it. As a structural steel I have defined the yield strength 250 and the Poisson's ratio 0.3 and all, and you could see the other parameters. Now you can choose the fixtures, right click on it and select the fixed fixture and just select the faces where you want to fix it. Practically these two faces will be attached to the bolt, right? And then you can apply the force by using the external force tab, and I'll be applying the force on this particular circular portion. You can even choose the direction by using the selected direction, the front plane. So here in the XYZ direction you can apply the loading. So let's say I want the 500 Newton into account, so it is approximately 50 kgs. If you want to change the inner system, go with the metric tree. So we'll be having the kg of 1 kg is equal to 1 kg, so 50 kg. Okay, that much load I'm gonna apply. So with this we'll check how exactly this entire wrench gonna behave, whether it's gonna fail or not. Before that I'll mesh it. There are different types of meshes available: standard curvature and blended curvature based. So I'll use the blended curvature based mesh. I'll define the minimum maximum element size of 1 mm. Okay, and you can just simply mesh the same. Once the meshing is done, you can simply run the study to get the results. Okay, these are the pre-processing stages which and all we have followed till now. Here you could observe the mesh distribution. Okay, so this is quite fine, no issues for me. Okay, well, so let's simply run the study to get the results in the form of stress, strain and displacement. Okay, and depending upon the system requirements, the performance will be different. Okay, so here you could see the stress results. It is crossing 1214 somewhat. Okay, let me just edit this chart. So it is quite difficult to read, right? So we'll define the chart in the form of user readability. So here I'll change the unit system to MPa megapascal. So if you want to activate the true deformation, you can use this true scale option. So automatically it is enhanced to 46%. The chart options, I'll change it to general and I'll define the decimals to 5 to simplify the chart. Even you can activate the show minimum and maximum notation so that you can just see where the minimum and maximum stresses are acting. in the settings you can use the different options. So here I'll use the mesh body so that I can even see the mesh. So now here mesh distribution and the even the one mesh stress you could set is 1200 plus, so the yield strength is 250. But the thing is, at a certain area it is acting more, so that point might be with respect to stress singularity, I believe. We'll cross check the same later. Okay, so here we'll see the displacement. So it is 0.4. Displacement is quite okay, no issues with that. The thing is the stress, a main concern. The strain sounds good, no issues there. So it should be less than 5% to consider the static analysis, remember that. So now in the stress, I'll simply turn off the mesh. You can simply use this option, hide mesh, and if I zoom in, you could able to see at this particular region there is a stress singularity, in the sense at a certain area stress is drastically more, so infinite we can say. Stress value is infinite at that particular location. This time instead of 50 kgs I'll go ahead with the 30 kgs. Okay, this is also maximum, so we'll work with only 20 kg range. I'll take the maximum 30 kg into account and I'll rerun the study and I'll again cross check the same. Before it was 1200 megapascal actually. Now we'll see with respect to 30 kgs what will be the stress distribution. So these are the basic steps. So instead of taking entire simple rectangular block into account and simply running the static analysis and showing the tools, it is not at all uh, but a method to explain the CA approach. So I'll take the practical example and I'm doing the same here. Well, the factor of safety also plays very important role here. So the factor of safety, which is applied load to the working load, we can say. So if a particular material has 250 yield strength, it should be less than that, so that the factor of safety should be more than 1. Okay, here you could see it is approximately 600 plus 607. So this is the elemental point or element it is which is failing drastically, so there might be the stress singularity. To avoid that, you can even make the fillets over there or make the design changes, or even one more way is to deal with this is to change the material properties. So yield strength is 250, I'm looking for 650 so that I can get the factor of safety 1 plus. So for this kind of components the factor of safety should lie between 2 to 6. That is the main criteria here with respect to manufacturing approach. So what I can do here is I'll change the material properties for now. Okay, so we have used the structural steel to this, so I'll try to just check which has the better yield strength so that I can take that material into account. So before that, I'll again showcase few of the tools here. So this is the section clipping. So here you can even just have the section of the results, okay, so that you can just compare the same. We do have the probe option. By using the probe you could able to define the certain location. Over there you can able to find out the stress value at a particular location or a point. So at that region it is 252. It is again more than yield strength. Okay, so again there are different tools, so we'll explore that one later. So here what you can do is you can set the upper limit. Let's say yield strength is 250. No, you can mention the same 250. So whatever the value is there below 250, you could see red region shows what and all the regions are there above 250, and we need to consider these areas into account to just make the modifications into this model, or if you want to optimize the design with respect to the stress right? So at that time you can like mainly focus on these areas to work on. Remember that this is how you can fluctuate your results options to get the approximation, so where exactly you need to modify. So remaining regions apart from red, green and yellow are safe to use. Okay, so let's say now I'll just make the modification according to the materials. Let's see which material has the better yield strength. In the SolidWorks materials we have the steel. So if I choose this one, ASI, and it has the yield strength of 325 and stainless steel of 172, too less. Plain carbon steel also less. Chrome stainless steel 172, no issues. Cast is also, yep, as I said, alloy steel it is 620. We'll take this material into account and we'll try to run the analysis. So we had seen the maximum stress is 607, right? Remember, stress is independent of material selection. Okay, and the displacement is dependent on the material, because with respect to the aluminum, brass, steel, the displacement will be different. Okay, so the Poisson's ratio will be also different, right? Poisson's ratio is lateral strain to the longitudinal strain. So according to this Poisson's ratio, the stiffness matrix will be solved to get the displacement. Remember that this is a very important factor to be considered. The partial differential equation Fh is equal to K into stiffness matrix. Sorry, that is stiffness matrix only into displacement we can take. Well, so now you could see the results. 620 is the 610. Okay, let me just plot the factor of safety. If I go ahead with the automated one, it is 0.84 again, which is not more than 1, so it is still uh, not safe for the working principle with respect to 30 kg. Remember that. Okay, now what I'll do is I'll cross verify the factor of safety, and same thing, the stress regions are same, you don't need to worry about it. You can even reset it to the original value. So as we have the yield strength is 620, you can just set it to automatic, so it will show the maximum stress. Okay, that is same. Singularity, remember that it might be working good with respect to the scenario, a certain location it is affecting, so we can make the design changes at that location. Let's say add pause or fillet or make some design changes. Okay, now let me just showcase the areas of concentration in the form of factor of safety. I'll define the upper limit as 6. Okay, up to 6 we're going to consider 2 to 6 range. Multiplication factor 1, and here I'll define the value 2. So I need the regions factor of safety below 2. Okay, so now here you could see, so these are the regions. Red regions are below 2 and blue are safe enough because it is under 3 to more range. Okay, so I need to take these red areas into account for the modification if you're going to just make the design changes or optimize this particular bracket. Okay, so this is how you need to carry out the simple static analysis. So that's all about the session. Coming to the summary here, we have gone through the static analysis. So we have applied the boundary condition, we have gone through the pre-processing stage, defining the loadings and the fixtures and getting the results, and we have also gone through the types of measures and how to deal with the results, that is float changes, and even the some of the few settings required in the float. and as well as we have seen the different probing options and the section views as well. So these all the tools will help us to get the results in a better manner. So using stress plots, displacement plots, and even factor of safety, these all the plots will help us to validate our results with respect to the practical approach. Yep, that's all about this session. Yep, thank you for joining and supporting. Stay tuned.